Hello everyone again and welcome to the DMSI channel, and it's truly a pleasure to actually have you all in this particular space. And in here we're going to explore a specific question that involves chemistry, mainly deal with general chemistry or inorganic chemistry. You will come across some questions that involves an atom and transforming atoms to ions. And in this particular case we have an example where you're going to be given a specific ion. In this case it's going to be calcium 2 plus ion, and you're asked how many electrons do this particular specific ion actually has. And it's quite interesting to actually think of this and also go back to the drawing board in terms of where is calcium 2 plus actually from? So looking at how you're going to plan your solution is really important to take a couple of things into consideration. Our goal in this video is to actually create a plan, and then the next thing is to actually execute the plan and also show two sides of how to solve this particular problem, looking at oxidation number, looking at also the Bohr-Rutherford's diagram, and also considering the quantum structure of these particular electrons in terms of their energy levels. So in this particular video here, we're going to explore the plan. And the first plan here we're going to explore is actually dealing with what are the things do I need to take into consideration for me to actually execute this particular problem. So first off, we know that calcium 2 plus actually comes from calcium, and this goes all the way to become calcium 2 plus ion. And so what are the intermediate steps that I need to take into consideration in order for me to actually solve this particular problem? So first off, from calcium, we need to look at where it is on the periodic table, and looking at the position on the periodic table, we're going to go into the next step, which is importantly determining which variables should I consider. Is it the number at the top or the number at the bottom? Usually we signify the number at the top as the superscript, and in this case is represented as A, while the number at the bottom, which is the subscript, is usually represented as Z for calcium in the periodic table and other elements on the periodic table. And then from these we'll be able to determine what the atomic number is for calcium, and from the atomic number we are going to actually get into the electronic configuration, where we're going to look at the Bohr-Rutherford's diagram and also looking at the quantum numbers and how those will be applicable to the electron distribution. And then finally we're going to actually arrive at the ionic state, whether we're looking at a process which is called oxidation or looking at the process called reduction, and saying which path does calcium actually pass through in order for it to become calcium 2 plus ion. So in this particular case here, we're going to look at our solutions, and first and foremost we're going to look at our part A, which involves let's look at the periodic table and actually determine where calcium is on the periodic table. According to this periodic table here, it says that calcium, if you scan through, is on position group 2. And in group 2, we notice in this case that if you look at other periodic tables, you actually have a particular representation that has calcium to actually have the top number, which is A, to be equal to 40. And A means the atomic mass unit of calcium, and for Z is considered to be represented as 20, which if you look closely at other elements, the smallest number usually and always is the atomic number. So Z is indeed the atomic number. And looking back, you need to know what atomic number is. Atomic number is when, in this case, the number of protons, which is the plus, is equal to the number of electrons. And for this to be true, you must have a what? Neutral. Let me bring this down. A neutral atom. So in this particular case, if the atomic number is equal to 20, which is Z, this means that the proton number is equal to 20 and the number of electrons in this case that we want for a neutral atom of calcium to be equal to 20 as well. So in this particular case, we are able to determine the number of electrons in a neutral atom of, in this case, calcium. So this part A, we're able to look at the periodic table, and from the periodic table determine what the atomic number is of calcium, and this focusing is going to be the neutral state of calcium. Now, from a neutral state of calcium, we need to then consider the next step, which is the electron distribution around a neutral calcium atom. So looking at the next step, which is looking at the electronic configuration, we're going to consider electrons because electrons are really important in chemical bonding and the behavior of a specific atom. So in this particular case, when it actually reacts with other atoms. So in this particular case, we're going to look at first, compare the Bohr-Rutherford's diagram to that of the other form, which is the quantum number Rutherford's diagram, and compare with the quantum electronic configuration. So let's look closely at what we know from high school, a little bit of high school, to now when you get into high school like grade 12s and also onwards. So for Bohr-Rutherford's diagram, which is mainly from grade 9 or so, we know that this is a nucleus and the first orbital here has 2 electrons, and once you go into the next level here, you have 8, where you actually add 4 first, and then you add the other 4 to pair up, and by so doing you go to the next level, and this level you also have 8 as well. Nope, erase that. Erase. Okay, while that is taking its time, let me just continue. Yes, it's back. This 4, and then you pair up, and that gives us a total of 18 electrons, and our final electron is actually going to be right here, so where we have 1 and 2. And so the final 2 electrons are actually on the outer shell. So as a result of that, our electronic configuration using the Bohr-Rutherford system is actually 2882. And looking at the other side, which is quantumly, in quantum state, we actually look at it differently, where we're going to show it in terms of, the energy level diagram, where the first orbital is 1s2, which is spherical and is pretty much close to the atom's nucleus. And then in this case, you have 2 electrons. Because I put 2, that is why that actually tells us that there are 2 electrons. But let's go, before we put electrons, you just put the other s. This is 2s. This is also spherical. And then we have 3p orbitals, and these 3p orbitals, they orient themselves in terms of the x, y, and z's, where the z, considering the coordinates, we can actually determine this to be our z, our y, and our x. And as a result, we have this, where we have in phase, out of phase, y is in phase, out of phase, and our z is in phase, out of phase. So that's our 2p orbitals. And then the next one here is going to be our 3s orbital, which is spherical but is a bigger sphere than the 2s, and the 2s is larger than the 1s. And this will then lead us to our next one, which is our 3p, which has its x, y, and z, but the lobes are bigger than that of the 2p lobes in this case. And finally here we have our 4s, which is a larger spherical lobe right there. And you're wondering, what happened to the 3Ps? No, we have our 3Ps, of course, but what happened to our 3Ds? Our 3Ds, we're going to consider those when we get into, the transition metal system, and how this is going quite different from the regular system of counting, and a really good help to actually guide you through configuration using the quantum system is actually looking at the periodic table. And we're going to talk about that, reading the periodic table, and how the arrangement of a periodic table is really instrumental in the beauty of naming various or assigning various configuration electronically using quantum system. So in here, once we go into this case, let's distribute our electrons. Of course, we have our lowest energy you have to fill, spin up, spin down, paired. That is fantastic. That is always the rule. And then the 2s, we also spin up, spin down. And this here now leading to the next one, where you have three orbitals that are actually the same energy levels. You have to, fill with one electron first, and then you pair up to give your balanced system of electrons to overcome repulsion of the electrons during this particular process. So in here, in total, we have 2 plus 2, that gives us 4, plus 2, that gives us 6, plus 2, 8, plus 2, 10, plus 2 here now, 12, plus 2. No, don't put 2 here first. Let's just erase that. And let's go with our system here. We have 1, 2, 3, and then you pair up 4, 5, 6, and then finally here we have 1, 2. So in total here, this is 3p6, 4s2. And in total, if you add all the number of electrons in this system here, you actually have in total 20. So in this particular case, we are able to actually represent a neutral atom of calcium in both Rutherford's and quantum electronic configuration. And so once we have this taken care of, the next step is, how are we going to transform our calcium atom into a calcium ion, calcium 2 plus? This actually, looking back, we know, looking at the electronic system of various ions coming from an atom. When an atom is actually on its own without any reaction, its oxidation state or oxidation number is 0 to start off with. Now, depending on what region you're going into, either negative infinity or positive infinity, the region starting from 0 you're heading towards actually determines the oxidation redox reaction process that that particular atom is going through. So in this part here, in this case, if you're going from 0 to the right, you're actually increasing in oxidation number. And either you're going from 0, or even if you're going from a smaller oxidation number in terms of, from negative to positive values, if you're going from negative to something more positive, it means that you're actually performing a process called oxidation, which means you are actually losing electrons. Let me remove the S because that doesn't make sense. You need one S. And in this case, I hope this is the right color. Yes, that's the right color. Losing electrons in the process here. However, on the other side, if you're from right all the way to left, this process is the opposite, which is called reduction, which means that you're gaining electrons, which means in this case you are actually decreasing in your oxidation number from 0 to -1, and so on and so forth. So in this particular case here, since we said that calcium is actually starting at 0 because it is neutral, and it is going to calcium 2 plus, this 2 plus tells me that it is actually losing two electrons. So to represent a two electron system here, you need to add two electrons. So therefore, if you balance the charge on the left side and the right side, it is actually equal because you need two electrons, two negative signs to cancel the two positive signs in order for we to have a zero right there. So in this particular case, we know that the calcium is actually performing a process called oxidative or oxidation reaction. Therefore, it is actually acting as a reducing agent in this particular process because it is causing the reduction of a specific atom, thereby itself becoming oxidized. So, in this particular case, let's change the color to something more appealing here. We have a couple of colors here that don't really line up. Yeah, perfect. So, this actually performs our process called oxidation, or it is oxidized. Therefore, it actually is in this case, calcium zero is a reducing agent. So all these key terms, you need to actually get to yourself familiar with it. And on future videos, we're actually going to talk a little bit more about oxidation and reduction, oxidizing agents and reducing agents, oxidized and reduced, and all that stuff. So once you have this taken care of, now what we need to know is this: for calcium 2 plus, it actually loses two electrons. That is our conclusion. And so if you're going back to your original diagram here for Bohr-Rutherford's diagram, I'm going to copy this, and let me copy here, and get this out of the way, get away, do it again. This should actually work beautifully. And copy, and we go down here and we paste it right here. Perfect. It means that for Bohr-Rutherford's diagram of, in this case, calcium 2 plus, it loses not only this electron, but also the outer electrons here. So as a result, this is erased, and is the two electrons are given to a specific non-metal. And this outer shell, once it is there but no two electrons, it means that the two electrons are out, and this actually is our new electron configuration of our calcium 2 plus. Therefore, we actually have the number of electrons in calcium 2 plus to be 2 plus 8, 10, plus 8 is 18 electrons. And so we're able, using the Bohr-Rutherford diagram, to not only determine the new electron count of calcium 2 plus, but also we can use quantum electron configuration, where if we copy this and we apply it here, copy and V. Excellent. So in this case here, our highest energy level that has the electrons right there will be lost in this particular system. So in the quantum electron configuration, this energy level, which is a 4s2, will actually lose the two electrons in that particular space right there. So therefore, calcium 2 plus now has a configuration that is represented quantumly as 1s2, 2s2, 2p6, 3s2, 3p6, and that is it. So therefore, adding the superscripts after the orbital orientation here, we are going to be adding 2 plus 2, 4, plus 6, 10, plus 2, 12, plus 6, 18. So we have 18 electrons as well. So it means that, yeah, both systems actually work in determining the number of electrons in a specific ion, in this particular case calcium 2 plus. So that is about it for this particular video. I hope you're able to understand this. I know it's quite a long video, but I hope that this actually helped you to not only see the two different perspectives of how to balance various reactions, mainly dealing with oxidation, but also how this is applicable now to the electron configuration, either using the Bohr-Rutherford diagram or using the quantum electron configuration, and also starting off with our idea of our periodic tables and the different numbers to take into consideration, and most importantly, how to plan out your specific a question in order for you to solve effectively in chemistry. So, thanks for following me through this. Truly appreciate it. Please hit the comment down below. Let me hear your thoughts. By that way, I can talk to you all soon. Stay smart. Please don't forget to subscribe to the DMSI channel and enjoy the rest of your day. Stay smart and believe in yourself.